Hello everyone, thank you very much for coming today. Again, saw you when you came in, gave you a wave. We're delighted today to welcome Associate Professor Olivier Girard to give a talk to us. I have some notes on Olivier to introduce him because he has done so many things that I had to write it all down to make sure I didn't forget anything. But obviously Ollie came and joined us as a Be-Inspired position within the school in human performance. So the talk today will be very much centered around human performance. Ollie got his PhD and 2 masters and an undergrad from the University of Montpellier in France. And then after that, he spent 8 years in Qatar at Aspetar Hospital, which is a sports medicine hospital and orthopedic center. And Ollie was in charge of some research there, which is great. He's also worked at Lausanne University and Murdoch, and we were fortunate enough to bring him over from Murdoch nearly 2 years ago, Ollie. Yeah. So if you jump on old Scopus and have a bit of a look at what Ollie's been up to, he's got nearly 150, or if you add his books to it, he's got over 150 publications. So he's been very busy. But the one stat that I did like more than the 150 publications is he's got 160 conference papers, which means that for every study he's done, he's been to a different location to talk about it. So he's done very well. I think COVID has only just started to slow him down. So Ollie's background is in racket sports and environmental physiology. And since coming to Perth, he set up an environmental physiology interest group. So we call it EPSI. And Ollie leads that group to talk about environmental contexts around exercise on regular times throughout the year. Ollie spent a bit of time in the Cirque du Soleil. You'll tell that from his accent. And of course, we've just had the $90 billion failed sub deal with the French. But Ollie has maintained his position in Australia, hasn't been called back by Macron yet. Anyway, I'm going to leave Ollie to tell us about his talk today. But thank you for joining us. You, mate.
Hi, everyone. Thank you for coming. Thank you, everyone, for tuning in online. So thank you, Cyril, for organizing this seminar series. Great initiative. Thanks, Pete, for the introduction, and thanks, everyone, for coming. So yeah, thank you for the summary of like what I've been up to. You put out some numbers, but probably the one I'm the most proud of is the collaboration. And this is over 300 now. So yeah, I really value that. So yeah, the purpose of today is just to give you an overview of what is my research interest. But really, like, if you feel like we can collaborate, just come and talk to me, and then I will be really happy to make this happen. So collaboration, this particular picture has been taken in Qatar 9 years ago, and that was kind of like a good example of like what I see as a very successful multidisciplinary research project when we assess the effect of playing tennis in the heat with different lenses, looking at thermal response, physical response, sleep quality, recovery markers, and so on. So really, I would like that at UWA, I can continue this sort of research to try to explore one particular problem and then give that different angle. So yeah, exploring the limit of human performance, and especially using sport activities. So if I can get this working. Yeah, that's what I'm trying to do. Bear with me. Okay, so now that you are here, like I like to ask you, right? Tennis, who's the greatest tennis of all time? Is it Roger? Maybe I should stop there, right? Yeah. That's it. Rafa or Djokovic? Roger, of course. Yeah. Well, yeah. Potentially. So surely there is a little bit of debate, but probably the one that is undisputed is Usain Bolt, right? And why is that? It's maybe because like he's the fastest man on earth, and there is some sort of fascination about like who is able to run as fast as possible. And let me put a bit of context in that. So this is an imaginary race where you have represented 116 years of Olympic history with the top 3 finisher for all of the Olympics, starting from the modern Olympics in 1896 up to the London Olympics. So Thomas Burke was the one winning at the time, over 13.5 seconds. And then, of course, you all know that Usain Bolt was having the gold medal in London. So it's quite impressive because if these two guys were to compete in the same race, it means that Thomas Burke will be 25 meters behind Usain Bolt when he was crossing the finishes line. So this is just telling us like how much things have been improving, better athletes, but also, I guess, improvement in technology and the sports science support that we can provide to the athletes. Some amazing stat also is that just imagine that now the current under 8 years old would have been gold medal if he were to compete with Thomas Burke, you know, at the time, just to tell you how much things have changed. And the under 16 would have been like silver medalist in Moscow just 40 years ago. So things are improving surely. And as sports and exercise scientists, we are playing a key role here to improve performance. So today we are here to talk about environmental stress. And I think it's indisputable that more and more major competitions are organized in conditions where it's hot or conducted at higher elevation than sea level. So good example include the Tour de France, of course. It's in July in France, it's pretty hot, but also some mountainous stage where some of the summit will be above 2,000 meters. But of course, if you look at the Olympics, in Tokyo, it was hot. It's going to be the same in Paris and then in Los Angeles and probably in Brisbane as well. Also, the Olympics in the winter is done obviously at altitude. So some of the challenge that need to be overcome by some of the best athletes. But also the football, right? In 2010, it was in South Africa that was organized at altitude. And of course, this one was quite controversial in Qatar because it was supposed to be organized in July, where in Qatar, is more than 50 degrees Celsius in this. So with that in mind, when I was working in Qatar, we had a chance to run some study to try to understand what was really the stress imposed on those athletes and was that a good idea in terms of the popularity and the safety of the athletes to organize this event in Qatar. So this is one big study that we have been doing where we invited the European team to come to Qatar and then play a football match, either in cool condition inside the Aspire Dome and then outdoor in Qatar, where as you can see, it was pretty hot in September still. We measured a bunch of things during the match and then also some tests before and then for 2 days to look at the recovery requirements. So what we observed is that the distance covered was decreased when you play in hot condition in yellow compared to cool condition. And this is mainly because the distance has high intensity and then the number of sprint is decreasing. But then it takes more time to recover. So the recovery after the sprint is longer when you perform in the heat. But the heat is not only detrimental, right? We also observe anecdotally that the fastest speed on the pitch was achieved when you compete in hot condition. So among the things that we measured the body temperature. You have here example of how we did that. We did that with ingestible pill in terms of measuring the rectal temperature, and then the muscle temperature was done immediately after the end of the game by putting some muscle probe inside the muscle, 3 centimeters, to understand what was the elevation in temperatures. You can see that it was about 1 degree higher in hot, in yellow, compared to cool condition in blue. But then we also observe the most important things to me is how we recover. And then I gave you one example here is repeated sprint ability test. So that's a test of human performance. Compared to baseline before the match, you can see that immediately after the game, they were slower on average to complete the repetition of maximal effort. That telling us that they are fatigued, right? But the interesting bit is that if you look at 24 hours, after playing the match in a hot condition in yellow, they already fully recover, whereas the full recovery only occurs after 48 hours in cool condition. So it was really interesting, and I think this is one of the lessons that we learned. We are thinking that, oh, when you play in the heat, it's going to be extra load, and then you will take longer to recover. But actually, we just observed the opposite. And then we observed the same thing for markers of muscle damage, also resynthesis of muscle glycogen was also not any different between the two conditions. Then with this in mind, because the Australian Open is playing in hot conditions, so we are also doing similar experiment for tennis player where we ask them to play for 2 hours in cool condition in blue and in yellow condition in hot. And you can see here the trends for the first hour, small break, and then another hour of playing tennis in the heat, where you can see quite clearly that elevation in core temperature, even so it's reaching hyperthermic level even in cool condition, but in hot condition, you can see clearly that they reach level that we would consider as quite of critical threshold of core temperature, right? And the interesting bit was really that the game structure was actually changed between the two games. When we look at the duration of the point, it was not any different, but the recovery between the points was extended by about 10 seconds in hot condition. So it means that they are able to preserve the quality of the game, but it's just that they need to modify the structure. And because in tennis, you can self-regulate to some extent, they took almost up to 30 seconds compared to 20 seconds in cool condition to recover. And again, when we measure different index of physiological disturbance or performance that is displayed here, you can see that there was an acute effect of fatigue when you play tennis in the heat, but then it was not any different between the two environments and the full recovery after 48 hours. So I guess the point I'm trying to make here is that behavioral thermoregulation is very important in those activities where you can self-regulate. Of course, when we are active, metabolic heat production will increase the core temperature, and even more so when we play in hot condition. But then this is also interpreted by the body as being discomfortable, right? When it's hot, we don't like that. So that in order to limit the buildup of the heat in the body, we employ some strategy to slow down. And some of them will be to extend the recovery, or as you can see in the football, to just perform less low intensity so that you are still able to surge to perform the most important action in the game. So really something is important, and I think this has also informed the work that was performed by our colleague Olivier for the Australian Open, where he showed, like with this rating system from 0 star to 5 star, that yes, the first one will be well hydrated to take some cooling strategy, but also we can also modify the structure of play. In tennis, it means that we might extend the recovery after the third set by 10 minutes so that the core temperature might drop, and then we feel better, and then we preserve the integrity of the game. I think we also need to perform some study in the lab, obviously, to understand more about the mechanism. And of course, when you perform an exercise in deprived oxygen condition, or when the temperature is higher, that's a big challenge to the homeostasis to maintain the effectiveness to different regulatory systems, the cardiovascular, the respiratory system, the brain, but also the muscle. And this will raise the relative exercise intensity so that hypoxia on the left is impairing the oxygen carrying capacity, and then in the heat, this is attainment of elevated temperature that might impair the performance. Something important to realize is that, and then if you just jump in the hypoxic chamber, you will figure this out straight away, is that hypoxia is an immediate stress to the body, right? There are some chain of reactions so that you can better cope with this stress. Whereas heat is going to impact the performance, it's going to decrease the VO2 max, but only once core temperature has reached a certain threshold. So this is not immediate, it takes more time so that the heat can manifest its effect. So we had this question, okay, why don't we compare this to stressor directly, right? Like, because there are some debates in the literature saying like, oh no, like heat is more stressful or hypoxia is more stressful, right? So we were like, okay, let's ask participants to perform an open loop task. So it means a task to task failure, cycling at 180 watts for as long as they can in control condition, in hot, in hypoxia, and then this one combining hot and hypoxia. And I'm sorry if the legend doesn't align, but on my computer was better anyhow. So the hot temperature was 35, the altitude was 2,500, and then obviously the black one would be when we combine the two. So as you can see, compared to the control condition, when you exercise in hot or hypoxia, you decrease by about 1/3. And we combine the two stressors, you further decrease. It was only 25 minutes compared to the control condition that was about an hour. So what was very interesting is that despite the fact that exercise performance was differently affected by the environmental stressor, yet all the measure of physical function, and this is neuromuscular function, for example, were similar, right? We stopped exercising at a similar decrease in force production capacity that is represented, if you like, in the red part here. So it decreased by about 10%, and this no matter was the duration of exercise. If you exercise 25 minutes or 1 hour, it was the same decrease. But the real world is different from the lab, right? So it's important that we also understand what's happening in the field. And something that is very important for team sport is the repeated sprint ability. That's a crucial fitness component, and something that was well researched here at the UWA with the work of Brian Dawson, obviously. So I thought I will just give you a little bit of background to understand what is RSA, or repeated sprintability. Well, this is this ability when, if you imagine one bar is one sprint, when you repeat all out sprinting with incomplete recovery, as would normally happen in the football pitch, for example, because the recovery is incomplete, then the power that you're going to produce after each repeated effort will just decrease. And then we need to understand what caused that, right? So what determined the repeated sprintability? Well, there are two components. Obviously, it depends on what you are doing during the actual effort, so the sprint performance, but also during the recovery between the efforts. So in other words, during the maximal sprinting, it relates to the energy supply and also the force that is going to be produced and applied onto the ground or to the pedal. And during the recovery, that relates mainly to the phosphocreatine, but also the metabolic waste removal. So in other words, it depends on neuromuscular aspect, but also on a metabolic aspect like energy supply and metabolic accumulation. So if we take the example of heat stress with a series of sprints, you have here represented 5 sprints that are repeated with incomplete recovery. This is why the performance is decreasing after each sprint. With yellow being with really hot, imagine 40 degrees Celsius, will be about 30 degrees Celsius in the blue one, moderate hot, and then cool condition will be, for example, 20 degrees Celsius. So what we would normally observe is that for a single sprint, actually sprint performance is going to be improved by acute heat exposure, because heat will act as a passive warm-up. It will increase the velocity of the reaction, and so we produce more explosive contraction, and when it comes to very short effort, usually performance will be improved. But then if we repeat this effort and then the core temperature is increasing, then we might be limited by the neural drive that we are able to send to the muscle, and so the slowing down in performance in yellow will be larger when you perform with excessive heat stress. And this is verified in the actual real world. If you look at this graph, this is representing for different athletic disciplines from the sprint up to the marathon. What will be the change in performance when you do that in hot condition above 25 degrees Celsius compared to cooler condition, which will be less than 25? And this is something very important to realize, is that heat is not always negative, right? For very short sprint, then in real world performer, like actually performance will be better if they are to compete in this hot condition. Middle distance, this is really the sweet spot, or there is no big difference. And then obviously, as the VO2 max decrease, then the relative exercise intensity is going to be increased, and so that we slow down. So that's why for longer distance, the performance is going to be impaired in the heat condition. And for altitude exposure, this is actually pretty much the same thing. The difference, obviously, is that the better sprint performance for the short duration event will come for the reduced air resistance. And clearly, this is what was observed in Mexico City in 1968, where I was not born, but surely that was, when we are interested in maximizing human performance, this is something that was quite remarkable at the time, that the guy was able, Bob Beamon, to just jump like close to 9 meters, which like put into the context at this time, it was more than half meter compared to the previous mark, which is just like record like this are not beaten by this much. Now we're talking about centimeters, but clearly that was quite impressive. And this is something that we were aware. And of course, like athletes, they start to prepare at altitude because they knew that's going to affect the performance, at least for the middle and long distance. But even with this in mind, you can see that the IOC was a little bit funny at this time. And then in the, I guess, like to maintain the equity between the different nations. So they have limited the time like that the team can train at altitude to 4 weeks before the Olympics. This is just like if you imagine now, like, yeah, it's going to be hot in Tokyo, but you're only allowed to heat acclimatize for 1 week. Right, so if you're training at the same time to maintain equity but preserve health, then you know, like you're in the middle of 2 days. So anyhow, so I guess from that time the concept of altitude training was born and popularized. So the classical method is the live high, train high. So this is, if you imagine you go to the mountain and then you're going to spend 2 to 4 weeks there. And the main idea is to try to improve the blood carrying capacity and get better when you have to compete at the altitude elevation or when you get back to the valley. But one of the potential drawbacks is that, of course, when you are training at altitude, you cannot maintain the same exercise intensity. So in the 90s, some American colleague came up with the live high train low, where you still live in the mountain to get the hematological adaptation, but then you go down in the valley for some session in order to maintain the oxygen flux and the quality of the session. But here in Perth, we don't have mountain, but it doesn't mean that we cannot apply altitude training. One method that is very popular, and especially now with the development of technology, is what we call the live low, train high. So it means that you still live in your natural environment. It's just that for a few sessions during the week, you're just going to jump in the chamber and then reduce the fraction of inspired oxygen and train in this hypoxic condition to try to improve your performance. And one of the methods that I've been particularly involved in trying to push is what we call the repeated sprint training in hypoxia. So this is this method where you perform all-out sprinting, I discussed, with incomplete recovery, but just that the oxygen condition in the room is going to be decreased. So you have here one illustration of one professional rugby team, actually the best one at the time in 2015, that after only 2 years of evidence from the research already started to use this training methodology. So that's a good example where the gap between the research and the application is quite short, right? So what they did is just that took the bunch of watt bike on the glacier in Teen and then just perform all-out sprinting in this deprived oxygen or lower barometric pressure actually in real altitude. So here's the first study that drive that training camp. So that's a study coming from Switzerland, from Professor Grégoire Millet's group in Lausanne, and they've been recruited 50 participants, so pretty solid study, training study. One control group that did no additional sprint, continued their training, and then 2 experimental groups that trained either in normoxia, in yellow, or hypoxia in blue. The training was for 4 weeks, 2 sessions a week, and 1 session looks something like this, 15 sprint organized by set of sprints. So 10 seconds on, 20 seconds off, and 5-minute recovery. I don't have time today to explain all what they've been doing, but today I'm going to talk about one of the performance tests, that is the repeated sprint tests up to task failure. So on the top, you have the group that train in normoxia, at the bottom, the group that train in hypoxia. So these are the sprint performance data before the actual training protocol. As you can see, the 2 groups, they are pretty well matched. Compared to the first sprint, one, they dropped the performance by 30%. They just stopped the test. This is what they call the task failure. So what happened after the training, right? After 8 sessions for 4 weeks? Well, you can see that on the group that trained in normoxia, on average, the power was increased by 6 to 7%. But they are not able to perform more sprints. So it means that after sprint 9, they drop by 30% and they stop the test, which is already a good outcome, right? If you're a coach, like if you improve performance by 7%, well, I would buy that, surely. And what happened to the group that trained in normoxia? Well, it's pretty impressive, right? You can see that, yes, they also improve the performance by 6, 7%, but they're able to reach task failure after this time 13 sprints, right? Compared to 9 before. So this is really like this study, I guess, that drive a lot of interest around on this methodology. But what we don't really know today is the driving mechanism. And this is where I'm throwing a call here. Like if some of you from the physiology department are interested in helping us to get some answer about why we are able to postpone the fatigue, these are some of the research that I will be interested in conducting. So yeah. This methodology is popular, as you can see on this map, at different places around the globe, using different athletes, team sport, rugby player there, here with the work of Paul Goods, also the female double pulling and ski, or in Japan, you can see that has spread. And just in 2017, so 3 years after the first study, you can see 12 studies from 6 different groups that show a clear benefit of doing this sort of training in hypoxia compared to normoxia. Now we have more than 30 studies, so pretty impressive, but it's mainly performance oriented and we don't really know about the mechanisms. So again, I think some work needs to be done here. Just to give you an example of applying this, so this is a facility available at the French Open in Roland Garros, where like when they saw the result of the repeated sprint training in hypoxia, they are quite interested to apply that for the tennis player. So they built this facility where you can play tennis, actually, I mean, simulate tennis, sorry, in this, and yeah, use specific movement and get better. So a lot of tennis players are now using that also in France. So we need to refine the best practice. So one of the questions to refine best practice will be, okay, what is the altitude to be used, you know? So with that in mind, we perform this sort of study where we just add different severity of hypoxia, so normoxia, moderate or more severe hypoxia, with repetition of all-out effort. And we observe that this is not linear, but this is only when you use more severe hypoxia in yellow compared to moderate or sea level in blue, that the performance is going to be decreased. The beauty also is that you can, when you use a running modality, to track the running mechanics and get an index of the mechanical constraint, which is also important when you want to prescribe training. This is some of the treadmill that we've been using. That's unique treadmill, only 2 in the world, where you can sprint on the treadmill while you are breathing less oxygen through this mask. And this is piece of equipment that we are looking to buy here to also be able to run this sort of studies. And then with this treadmill, we can measure the ground reaction force. So why this study was interesting? Because we're also able to quantify the fatigue. And how we quantify the fatigue, this is by using some electrical nerve stimulation, for example, on the femoral nerve, and then quantify the force that's going to be produced by the muscle. So if from before the exercise, the force produced is going to be decreased, that's a clear sign that the muscle contractility, the force production capacity intrinsic of the muscle in resting conditions, so when there is no command from the brain, is going to be decreased. So as you can see, no matter what the condition you perform the sprint, there was clearly a peripheral fatigue, and this is a big limitation of all-out repeated effort. But what we observe is that when you increase hypoxia severity, the peripheral fatigue development is actually larger compared to condition where the hypoxia severity is less. And that's very interesting. So it means that we create more muscle disturbance, so presumably a stronger training stimulus. Even so, the performance impairment will be more in more severe hypoxia. So yeah, we produce less external work, but even so, we produce also more like disturbance to the muscle. So it's kind of like a chicken-egg relationship. So keeping that in mind, we're trying to do some work to really maximize the training stimulus, but at the same time maintain the training quality. And how we did that, we try really like interesting stuff with teams that believe that they can get better by using that stimulus. So with the French rugby, those girls, they got the silver medal at the last Olympics. So, and they're really asking for new training modalities. So we have been testing things like repeating all-out effort at 5,000 meters. So it's only 11% of oxygen. So that's quite stressful, but we are careful that we preserve the training quality by asking them to come outside the chamber and then perform the between set recovery in normal condition, so that we can really stress the system during the actual effort, but then allow them to recover between the efforts so that the training quality could be maintained. So this is a video of how we did that. So again, all out effort, there is no cheating for sure. You don't need to think like how you can pace that. It's just like full on for a few seconds and you recover for 25. And then, yeah, when you've been doing like 4 to 5 sprint, which we call one set of sprint, then you come outside the chamber for 3 to 4 minutes to recover, refresh, and then jump back in the chamber. Immediately, the saturation is going to drop within 30 seconds. At this altitude, we will be close to 70%, and then go again for that. So this is how they have been using that just before going for the competition in Dubai. So yes, team sport, they need to be quick, but they need also to do that for a long period of time, right? Like in football, 90 minutes and so on. So yes, I've been talking about some of altitude training methods that will improve the local tolerance for the muscle. But of course, we also need to improve the aerobic capacity, the blood carrying capacity. So we also may want to use more classical training methods, those where we spend significant amount of time. When I say significant, will be several days to several weeks at altitude or severe or simulated altitude, so that we can also increase the hemoglobin mass, for instance. So this is a paradigm that we wanted to test that we call the live high, train low and high. So how we did that, we invited the large team of team sport to Qatar, and then we divided in 3 groups. So the training camp was for 2 weeks, and we tested them before, immediately after, and then 3 weeks after. So here you have the 3 training group. The first one will be, if you like, the control group, and then we had 2 experimental group. So in Qatar, lucky enough, we had 25 dormitories. So a lot to accommodate athletes to sleep at altitude. So the two experimental group, they sleep at hypoxia and they accumulate about 200 hours of exposure to hypoxia within 2 weeks of exposure. In terms of practice, they all train together near sea level. Kata is like close to sea level. And then the two experimental groups, they also perform additional sprinting. The difference is that the group in blue, the live high, train low, and high, perform the all-out sprinting in hypoxia compared to the group in yellow that perform the additional sprint in normoxia. How this was performed? Well, you can see this crazy piece of equipment. And then if you have the close look, this looks something like this. This is 45 meters long that you can install anywhere on the pool or for the team sport on the ground. And then you can see that you can control the oxygen, and then it's ecological. The athlete, they can just perform all-out sprinting on the ground in hypoxic condition and train this way. So they have been doing that for 6 sessions for 2 weeks, so 3 sessions a week, with one group doing the hypoxia and group doing normoxia. What did we observe? Well, as expected, the control group had no change in hemoglobin mass, the blood carrying capacity marker. And the two groups that spent 200 hours of exposure to hypoxia, you can see that hemoglobin mass will have increased by 3 to 4%, and that was maintained after 3 weeks. This is something that is expected. Hemoglobin mass, unfortunately, it takes time, and by about 100 hours of exposure, the general figure is that you can expect 1% increment. So this is roughly what we've been observing. But no difference between the sprint, hypoxia, or normoxia. Here's the performance, and this is the interesting bit. You can see that compared to before, after the camp, the two groups that train with additional sprinting got better, like the cumulative time was lower, but that the group in blue, that's the group that did the sprint and hypoxia, got twice larger gain in performance compared to the group that trained in normoxia. And also, they are the group that after 3 weeks were able to maintain this performance improvement, whereas the other group came back to what it was before. And to my knowledge, that's the only study that was able to collect muscle biopsy. That was quite difficult, but we managed to obtain muscle biopsy in this sample of athletes. Some of them were Olympic standard athletes. So we took muscle biopsy. We observed no change in the control group that did additional sprinting. Here are the data for the group that trained in normoxia. So anything on the right-hand side of the dot line means like you are upregulating this particular metabolic pathway. So yeah, when you do all-out sprinting, that's positive, right? You can see that like pretty much all the markers, they are upregulated. But when you look at the group that train in hypoxia, you can see that especially for the oxygen sensing carrier and the mitochondrial biogenesis marker, you can see that especially from pre to immediately after on top, and at the bottom, this is from pre to 3 weeks after, you can see that, yes, it was some upregulation. So I think we have some clear evidence here that some of the performance adaptation are really coming from muscle adaptation. But again, to my knowledge, that's the only study that employ muscle biopsy, and then we definitely need to learn more about that sort of adaptation that might occur after this sort of training. Talk about heat, talk about hypoxia, but how if we combine the two stressors, would that be better? Well, I guess some teams are aware of that and starting to implement combined training camp where they going to turn up the heat to increase also the tolerance in the different stressor, or just to get better in normal condition. And you can see in the literature that there's a lot of studies coming in, but also the elite athletes, and this is something that's done also at WACE with my tennis PhD, that in preparation of major competitions, such as the last Rugby World Cup, the Welsh Rugby, they have been both using heat training by going to Turkey, but also going for 2 weeks in Switzerland to also try to increase the hemoglobin mass. So in other words, try to get the best of the two worlds. So again, we have been trying to bring some answer to that question for a long time. And this is a study that, to my knowledge, that's the largest ever published with elite team sport athletes done with the French Rugby, where we had different group training in different conditions. You can see the group training in the heat, obviously, with measure of the core temperature here with the thermometer there. And yeah, it's a bit complex. I will not go into the detail, but what you need to remember is that those athletes are truly elite athletes. They would train 3 times a day. So rugby practice twice a day, plus like every morning, one conditioning session that was either continuous exercise or repeated sprinting. It's just that we did that in different conditions, right? So here are the results. We had 4 groups. The camp group is the group that did all the intervention, but had no environmental stress. They did the continuous in 20 degrees Celsius and the sprint near normoxia. We had the heat group that had heat only. We had the hypoxia group that trained at 3,000 meters. And we had the heat and hypoxia, the lucky group, that combined the 2 stressors. And this is what we observed. And we were a bit disappointed because we were expecting that, well, the group that combined the 2 stressors, we were expecting that they will get better than the others. But in reality, we observed that if you use 1 stressor alone or the 2 stressors, there was no difference. Well, there's some good news here. Like the good news is that all groups, they improve. So it means that training is working. And this is really a good news, right? Even in this like top elite athletes, a 10 days training camp is going to improve the performance. We have represented here the VO2 max, but that was true for all the tests of performance that we've been doing. But again, I like to draw your attention on the fact that it's a lot of inter-individual variability, and then we need to be very careful when we work with athletes to look at this value, but just to consider the spread. So it means that for some athletes, it would be better just to be performing the training without additional stress, but for some, you would need to stress more the system to get more adaptation. One particularity of this study was that we used the heart rate clamp approach. So it means that we tried to get the same heart rate no matter what the training environment. And what we could figure out, and that was not something that we did intentionally, but just something that we have been reporting and found very interesting, is that when you clamp the heart rate in the heat, the power that you're going to produce on the bike is only 3/4 of what it will be when you perform the same in control condition. So that's quite cool, right? You get the same cardiometabolic stimulation because you control the heart rate. It was 70% of the heart rate reserve, but it's just that in the heat, the power that you have to sustain to reach this heart rate was much lower. So in those athletes, when you have to train during a very intensified period of training, that's probably something that you like to consider. So this brings me to the last point and the concluding part of this talk. Try to extend the knowledge again from high performance sport to try to apply that different setup, either for the injured athletes, what we call the load compromised athletes, but also for a broad range of clinical population. So of course, it's a long journey when you get injured for the rehabilitation before you can get back to the pitch. And you can see all the tools that you can employ to try to minimize the loading and have a progressive loading up to the point where you can fully load the lower limb system and all the training adaptation. I'm not sure if you're familiar with this tool. This is Alterg System. So basically, this is a system that with some pressure will allow you to unload your lower limbs. So compared to having the full body weight, you can unload up to 50%. So you only have to support up to like half of your body weight, which when you're in the rehab phase could be something quite successful. And what is measured in this is the vertical force. How we measure that? Very simple. With some insole now, we can measure what will be the vertical force. The data, they are represented in how many times your body weight. So usually when you are walking, it's about one time your body weight. And of course, when you start to run faster, then it can be like up to 2 times your body weight. In top sprinter, like would be like almost 4 or 5 times the body weight, right? They can apply, but this is what they have been observing. But what is very important is that when you unload the body, you can see that the vertical force is going to be decreased by about 20%. But also when you reduce the speed, the same thing is happening. So it means that if we have different combination of body weight and speed, then we can get different mechanical constraints that will be indirectly evaluated by the vertical force. So just to give you an example, for 2 times the body weight, you can run full body weight at 10 km an hour. It will be the same mechanical constraint, roughly, than if you run faster, 14 km an hour, but only 70% of your body weight. So this is the beauty of this kind of tools, but this is very expensive. So what can we do? Can we perhaps use environmental stress to create the same benefits, right? To unload the body weight, but still get the cardiometabolic benefits of exercise and not lose fitness, for example. So this is work that is ongoing, and then that is something I'm really interested in. So if we take the same example of this runner at 14 km an hour and near sea level, well, if he's recovering from an injury, he might not be able to sustain, like this speed because it's going to be too stressful for the lower limbs. So what can we do? What we can do is, well, ask them to run slower, right? Like compared to 14, just slow down, run at 10K an hour. Cool. But what you don't want is to have a corresponding decrease also in the metabolic stimulation, right? What you want is to maintain the stimulations. And this is how heat or hypoxia will be very useful. Yes, we can reduce the treadmill speed, but then with hypoxia, with the stress that's imposed on the body, it means that we might be able to run actually with the same heart rate, but less mechanical constraints. So this is where this is becoming very interesting. These are studies that I've been doing in Malaysia. This is instrumented treadmill, the Bertec one. Obviously, we have one Bertec treadmill here, and then we are trying to work hard to try to fix that. So hopefully, once that's fixed, we can run this kind of studies back in our biomechanics lab. So yeah, clinical population. When you're overweight, when you're suffering for osteoarthritis, osteoporosis, ambulation might be painful, right? And if it's painful, then you might not engage in exercise because this is not particularly pleasant, right? So something that we might want to do is just to limit the mechanical constraints. So ask this lady to just walk slower, but then by using hypoxic exposure, we can rise the stress on the body and maintain the cardiometabolic stimulation that will be needed to get the benefits of exercise. So this is really some work that I'm really keen to be doing. And yeah, we have a lot to learn from the psychologists, and the king one is obviously Freud. And I like to use his analogy of the iceberg here to say that, yes, elite sports is important. This is something that I'm personally interested in, and the high performance sport group, surely. But what's under the ocean? Well, what's under the ocean? This is the therapeutic use of hypoxia. And I think we can apply some of the knowledge that we learned from the elite athletes to some of the diseases to try to improve the condition even better. So decrease the blood pressure, improve the blood profile for type 2 diabetes, for all the adults to better maintain the explosive force that is well correlated with the risk of falling. Some fascinating research with the spinal cord injury to increase the corticospinal tract excitability that we can assess with transcranial magnetic stimulation, or with obesity to better control the weight, in addition to obviously the rehab. So I know that in this room, a few students are working on that topic, and then we are very keen to extend that and improve the best practice, but also at the same time to get some mechanistic answer about what this might be working. So this is my conclusion. I think we are at this time in point where we have two options. The classical one, and this is the one that we have been using for years, is that, yes, we perform the same exercise, but by using an additional stressor, so think about the heat, for example, then the exercise response is going to be more stressful, so the core temperature elevation will be higher, and so on. And if you repeat that training stimulus, then eventually in time you can get better. But the new view is that maybe we don't need to do more work. We don't need, because like it's not pleasant, and for some clinical population, this is not something that is achievable. So what if we just perform the same exercise intensity? Let's think about the heart rate, right? We exercise at the same heart rate or at the same perceptual response, like with the rating of perceived exertion. But it's just that with hypoxia, we can do that at a lower running speed, walking speed, or power that you produce on the bike. So I think there is an opportunity here to work as a broad group of physiologists, biomechanists, also like psychologists, to understand also like how pleasant is the exercise and so on. And then using this transdisciplinary and holistic approach to try to bring some answer for the patient so that we can improve the exercise tolerance. Right, so that's it for today. So again, thank you for engaging, and hopefully this will lead to some cool research that we can run together. So thank you.
Olivier, that was really lovely talk. I have two questions actually. The first one is in relation to the hypoxia training, where you're looking at individuals who have particular diseases that may have an inflammatory basis. Are you concerned at all that the hypoxia may actually induce inflammation, or even longer term, that actually might impact those conditions more severe as opposed to being beneficial?
Yes, it is. And this is why I want to work as a multidisciplinary team, because often we try to make things better from our perspective. So from the exercise physiologist, yes, you can develop a training modality that you think will give better result, but there are some side effects. And then of course, like inflammation, especially with disease population, is one of them. And this is not something that you want. So by trying to fix a problem, you don't want to create more problem, right? So this is why we need to, by refining best practice, to take a more global approach to understand what would be some of the upregulated and potential downsides and that you want to limit. But yeah, surely, like it's well described that with obese population, when they exercise, and even so when you add hypoxia, this is an additional stressor. So surely, like you need to consider that. And then, you know, like one stressor and one stressor is maybe not two, maybe that's 3 or 4, you know, like, so if it's an additive effect, this is where like it might be. Yeah, so how to learn how we can modify the exercise structure maybe to make this limit the increase in the inflammatory response, maybe extend the recovery, like, you know, in terms of when we plan the sessions so that we don't reach scenario and, you know, yeah.
And I just want to just ask the second part is that the question I had before actually was about a lot of the people that you're examining or from the other studies appear to be relatively young individuals. And relatively now as well. And it sort of relates to the inflammatory processes that I wonder if there's a long-term influence of stressing, because these are athletes, so they're going to be doing this type of training for long periods of time. During a time in their life where they may not be predisposed to certain diseases. That'll come later in life, and some of those have a real inflammatory basis. So it sort of has that same thing about, you know, you may not actually see that effect in some of those individuals in those groups because you may see it down the track later.
That's why we need to conduct some research to the specific population and also in specific context. You're right, like most of the study have been doing in healthy young male. But what, like, if you implement that in somebody that is not used to training, you know, so we might want to have first a lead-in period before we actually like implement the hypoxic, which would just make a difference between what is really due to the stress of just exercising if you have been doing nothing for a long period of time, and compared to when you start to add that, how you periodize this and all this kind of thing. Sure. That's excellent. Probably depends on the dose, I guess, and yes, finding the right spot. But the difficulty is that, you know, hypoxia is usually prescribed, and Jackie, you know that because you have been working on that by using like a fixed external like stimulus where we decrease the oxygen fraction, but it doesn't mean that's going to be the same stress for every individual, right? We don't individualize that, you know, like by measuring like the internal load. We just like impose that and presume that's going to be the same stress when you simulate altitude at 3000 meters. But the reality is that it's very different. So yeah, we need to better understand that, surely.
Yeah, I mean, you're right. I don't know if it
Sure.
I was just wondering if you've done any of this kind of thing, or if anyone is on people that are actually adapted to high temperature environments rather than acclimated to high.
No, not that I know. People that are already heat acclimatized and then.
No, people who have for a long time lived in very hot environments, adapted to the long-term acclimated.
Yeah. Well.
Aside, including John C. people from South, what's one in South Africa, people who lived in quite high environments and are quite active. It would be interesting to know what their profiles look like. It's very European, and it would be interesting to know how the reaction norms for humans as a a group look relative to the reaction norms for high level European athletes?
Yeah, I know in hypoxia, like there are some studies, of course, comparing people living in the Andes and different part of the world with mountain. But for the heat part of things, I'm less familiar with that. And in our study, actually, one requirement is that they are not heat acclimatized before they start experiments. So that's why, like, we basically like flew them to the Middle East, you know, like so that they are not exposed to the heat before they actually like start the protocol. Sure.
Thanks, I really enjoyed that. I was interested in the biopsy data that we showed, and you high, train low.
And high.
And yeah, and that, you high, train low one. It was interesting because in mice and MHC1 and 2X both showed an increase in gene expression. And typically you think about endurance versus strength training, and you get one or the other. So it's really interesting to see changes in both, although doesn't necessarily translate to protein expression, but the other one, you did high, train low, train high group.
Yep.
They only seem to show an adaptation or a change in the HC1, slow mice. So I was just wondering whether you think that might be because of the predominance of the hypoxia or the additional hypoxia element there, and is there a trade-off between that adaptation between different phenotypes?
That might be one difficulty is like the team sport population, they are like so diverse, you know, like, so that might also well depend on the who was actually in each group, you know, like it was a population of field hockey player, which of course they have different position on the field. And so because of their different position, you can imagine that they have different like phylotype distributions. So with that in mind, when they receive this hypoxic stimulus, they might respond better than others. And it was a little bit of variability there. Find a bit of money and surely like that will be some of the cool things that we can be doing. Yeah, again, that's to my knowledge that the only study that's been looking at this like regulatory pathway, so we need more work there, and you know, happy to chat about this.
I think we have a question online. It's more of a comment than a question. Oops. Yeah, can you comment on the effects of sex?
Yeah, we know a little, like the only study like out of the 30 available there is the only one with the French rugby. Actually, like all of our knowledge is derived from young men, you know, so it's hard to I don't know if it's like any different from any other sort of exercise, you know, like, but yeah, it's hard to answer, like, I'm sorry, but like there's only one unpublished study there. So nobody has directly compared, you know, like hypoxic tolerance for this kind of exercise between male and female.
This idea of reducing load by imposing additional stress, I think that's a really good one, because even hypoxia means some additional equipment. I just wonder if anyone did breath hold. Breathing more long breath.
Yep.
How do you control?
Yes, so this is a method that is called like hypoventilation, voluntary hypoventilation. So as you described, this is something where you're gonna just like expire all the air and then just hold your breath during the sprinting part and then just like catch your breath after the sprinting. So yes, this is the hypoxia, the cheap hypoxia. So yeah, this is part of the panorama of the hypoxic training methods. So I think this is only working if we create a stress on the body, and then how we measure that is with the saturation. And this is where it was some concern that like, you know, that might not be sufficiently stressful. So at the end, like, you know, it's not working. But with the continuous monitoring in both swimmers and in rugby players, they have been showing that actually like the saturation is dropping, and it's dropping between the sweet spot that is between 85 and 90%. So yes, to answer your question, that's working. To my knowledge, there are 4 or 5 studies that have been showing that it's provide additional benefits compared to normoxia. To my knowledge, no direct comparison with hypoxia, but yes, it depends how you structure the exercise so that you can spend significant amount of time, like in these sweet spots, and this is why it might work. But yeah, I can direct you to some of the studies that have been using that. But as you say, the success is probably like how you incorporate that, like how you teach your athletes, to run that properly. But yeah, there are a few studies.
One more. Thanks very much. But the effect of hypoxia, I think, at the systemic level is probably more relevant than what's happening at the mitochondria, which is hard to see. Making the hypoxia so it's very modest, the effect of the mitochondria. Now, that does have an effect of the stiffness of the mitochondria, but it's probably more of a systemic response, particularly to an untrained person, which really the mitochondria is simply oxygen. So the PO2 stays quite high inside the muscle relative to a trained person. So sort of benefit might be coming from what's happening centrally. It's just a comment.
Yeah, for sure. Like, I mean, you're talking about the vasodilatory compensation that's happening, like surely it's something that might explain why you get better. But again, like to my knowledge, there is no single study that look at that, like we measure the flow mediated dilation before and after, which is the only like measure that's been reported, but we didn't see any change, but it doesn't mean that it's not a potential mechanism. It's maybe because under our scenario was a short training camp with only 4 additional sessions, so that might not be enough to change this sort of response, surely. But of course, like the cardiovascular system and the oxygen delivery and the blood flow will play a major role, like for explaining some of the improvement after this. So after the question is whether like hypoxia will add something additional, and then just depend on how you structure the exercise combined with the severity of hypoxia. This is only when you might see an additional benefits compared to just doing the exercise only.
There's one more question on Zoom, and I guess then we have to wrap things up.
Sure. Well, is the question about using the mask while we're exercising? Well, I think there are some study with this training mask like that pretend that it's same like hypoxia, and then the level of evidence in my reading is not, for the reason that I was explaining, like compared to holding your breath where the saturation is dropping, and then yes, this is a physical stimulus. Wearing mask, it's not, like the saturation doesn't drop. Like it might be a good training for the respiratory muscle to some extent, but this is not dropping the saturation. So the short answer would be that no, would be better to hold your breath than just like use the mask.
Thanks again, Olivier, for this very accessible overview of your really fascinating research.
Thank you.